Okay.
Okay, so you are...
Yeah. Enlarge it.
Okay.
Okay. Oops. Like this. I like try step by step every like little region of the poster. So in this work, which is quite introductory, we try to apply to graph neural network architectures a reasoning we had done before in another article about convolutional neural networks. And in particular, we tried to introduce a thermodynamic analogy, treating like the parameters, the weights of the neural network, as like non-quantum and non-relativistic particles. And we wanted in particular to introduce a concept of temperature which was really thermodynamical guided, because normally temperature is defined as the like the learning rate on the batch size, because it's like related to the like a sort of stochasticity and the noise during the learning. That's why it is introduced like this. But we wanted to make a more strict analogy with thermodynamics. And in particular, we associate to each parameter a velocity, which we define as the difference between the value of the weight among steps inside the epoch or among epochs. And in our experiments in this article, we consider the difference of the value of the parameter between epochs. And the value of the parameter is just considered as the position of this particle in the analogy. And the instantaneous temperature is defined as the mean kinetic energy of the parameters, when like by simply setting the mass to 1. And the temperature at equilibrium, so the thermodynamic temperature we consider, is calculated by averaging over the time steps we consider, in this case the epochs, when the training has finished, so when the loss and the accuracy no longer change, which is like our condition of equilibrium in the case of neural networks. In this article, we consider two different architectures. One is made of GCNs, and the other one considers also graph attention networks. Those architectures are quite simple, with a few layers, and they are trained on MNIST superpixel dataset. We trained the architecture for 600 epochs, and after the 600 epochs, we start our thermodynamic analysis. We train the model further 100 epochs at equilibrium, and we focus our thermodynamic analysis on the last 100 epochs at equilibrium, when the train has already finished. And in particular, we want to attest the dependence of this temperature, so this mean kinetic energy at equilibrium, with respect to the learning rate and the batch size. And we do it separately by fixing first the learning rate and changing the batch size, and then fixing the batch size and changing the learning rate. In these graphs, pictures, you can see the dependence of the temperature for different layers on the learning rate and on the inverse of the batch size. And in particular, this result of the temperature is of course averaged on the epochs, but also on the parameters of the layer. And we can see that for the dependence with respect to the learning rate, it is not linear, as it is stated in literature, where the temperature is, as I said, learning rate on batch size, but it's quite parabolic. On the contrary, for the dependence on the inverse of the batch size is quite linear, and this is in line with what is stated in literature, but is different from another result we had obtained on convolutional neural networks, in which we had a nonlinear behavior both for the learning rate and the inverse of the batch size. What's more, we also wanted to see the behavior of the parameters inside one layer by just plotting their mean squared velocity. So we do not compute the mean over the parameters, and we show their mean kinetic energy like for each parameter, for each weight in these two plots. The plot on the left is obtained by flattening the matrix of the first layer, of the first GCN layer, and the second one is not flattened. And we can see that the parameters of this weight matrix, which is used for the embedding in the first layer, are not showing the same mean squared velocity. And we had obtained a similar behavior during the study on CNNs, in which we noticed that different filters of the same CNN had completely different temperature. So some filters had really high velocity for the parameters, whereas other filters had really low velocities and the parameters had more or less the same behavior. Here we recognize that it seems like that different rows of this weight matrix has different temperature, and what we think is that with a connection with what we discovered with CNNs, where we tried to use this reasoning of temperature to prune the parameters, because during the study on CNNs we discovered that the cold filters, so the ones that had low velocity, low temperature, were the strongest in learning, because if we eliminated, so we pruned the hotter filters, so the ones with the highest temperature, we discovered that the behavior of the model was the same. Maybe I was confused, but maybe I can explain it better. So the concept is that this thermodynamic analogy allows us, in this case, by looking at the velocity of the parameters, to see that some parameters really change a lot, even if the training has finished, and have an high variation. And we see it here for the GCN, but also for the CNN, in which we actually discovered that by eliminating cold or hot filters, we had completely different behavior. The elimination of the cold filters really caused a high change in the performance by lowering the performance, because the cold filters with the lowest velocity were the ones that really were learning something, because they were not variating anymore at the end of the training, whereas the hot filters can be eliminated without any change of the performance. In this case, we still have to do this pruning experiment on GCN, but it was interesting to discover that also in this case, we can notice that different rows of weights show different variation of the parameters. And one interpretation or one experiment and useful thing we can do is that we can use this fact to introduce a pruning technique, and so also maybe reduce the embedding dimension for the features, or also ease the optimization of the network, but by reducing the number of parameters. In this other region of the poster, I simply show the same results by looking at the dependence of the temperature from learning rate and the inverse of the batch size for the other architecture, including GATT convolutions. And we actually obtained similar results to the GCN architecture because the dependence of the temperature from the learning rate is parabolic again, and the one from the inverse of the batch size is linear and only like between linear and parabolic for the final linear layer. This shows that like the like notion of temperature introduced and used in literature is not we do not reobtain it by like with this other definition of temperature, which is thermodynamical guided, and that different layers like behave independently also. They are not behaving in the same way in their dependence of temperature from these hyperparameters. And that was all, more or less. The most important next step is to apply a temperature-based pruning technique on these graph neural networks architectures, as we did for the convolutional neural networks, and which unlikely I cannot show you here now, but in the poster session, yes, tomorrow. Yeah.
Do we have any question? No? Yes.
So you're using, thank you for the presentation. Are you using Adam or Adam?
Yeah.
What are you using?
Adam Optimizer, yeah.
Okay. And
By
this, okay, and this fact that you should have a linear dependence on the learning rate comes from a particular algorithm that you are using, right?
Can you repeat it?
You
Sorry?
said that in the literature, I guess that you're assuming some specific algorithm dependence on the learning rate, right?
You mean,
So
sorry.
how this temperature, so the gradient of the weights should depend on the learning rate?
You mean this, this relation here?
Or what you were commenting on this right-hand side in the middle of your poster. So this dependence on the learning rate of your temperature.
No, I'm not sure I got your question.
So you were saying that in the literature it is known that this temperature should depend on the learning rate in the linear fashion.
Like it is stated, yeah, because like it's more like I didn't like I never saw like actual experiments measuring the temperature, but you know, from a theoretical point of view, this temperature is introduced as a mere analogy with thermodynamics. So the concept of temperature is used in a theoretical analogy without any measurement on the neural network, because if you like, you can imagine that if you see those parameters like moving stochastically during the training, if you enlarge the learning rate, of course this is more stochastic, more noisy, and in the same way, if you like diminish the dimension of the batch size, in the same way it's more stochastic. So the temperature is only introduced like this this fraction of learning rate on batch size with a like to do a reasoning like I don't know, guided by a reasoning on stochasticity and the noise of the parameters during the training and during stochastic gradient descent, but there are no measurements. Like I don't know if.
Okay,
like,
I probably get more to you back during the coffee break.
Okay.
Yeah, but I mean, you are training Adam Optimizer, or you are using stochastic gradient descent?
Stochastic gradient descent with Adam Optimizer.
With Adam, okay.
Yeah.
Yeah, I see. Good. And then actually, you say in some point, and I'm sorry, you have more questions? No. In some point, you say okay.
So in the last figures, so on the right side, basically, if you maybe scroll to, yeah, I've noticed that you're dealing with extremely low values there. Right?
Here. Yeah.
So, so I was wondering, are you using a double precision in your whole framework, so that you know, can basically tell these low values apart, or are you using single precision for the training, which is standard in PyTorch usually?
I think I'm using the standard, yeah.
Okay.
Thank you for the question.
Yeah. Thanks for the freestyle presentation.
So, have more questions? No. So, I have one comment. You say in some point you use a pooling. I mean, you say
Yeah.
that, but I mean, changing from max pooling to mean pooling is already including like parsimony in the decision, because max pooling is taking only one of the.
It's like a concatenation of min pooling and max pooling
Oh,
together.
you're using both.
Yeah.
Okay. That was clear for me. Okay, thank you. Okay, so let's thank our speaker.